Hello. Over the last 2 weeks, you've been gathering results from an experiment, plotting a graph, then modifying those results by, in this case, squaring the times to plot a new graph, and you should now have ended up with a graph that is a straight line through the origin. And the reason we did all that is that it's much easier to analyse that sort of graph than the first graph you drew, which was a curve. But why do we draw graphs at all in physics? Well, there are a few reasons. One, it's a way of quickly representing your data in a way that can be interpreted roughly. You can see a graph that's showing something getting bigger or something getting smaller, and that's just a simple representation of your data. Secondly, we can use it to identify patterns and trends. If we, let's say you're doing an experiment and stretching a spring, and you found the extension of the spring with 1 Newton and 2 Newton and 3 Newton. If you drew a graph, you could work out what the extension would be for any value in between that. So you don't have to measure every single result. You can use your graph and a best fit line to estimate or predict what other data is going to be. But today what I think about is using a graph in conjunction with a formula to allow us to work out some value in that formula. All the graphs we plot in physics are representations of real-life phenomena. Some of these graphs you'll be familiar with from GCSE, some might be new to you, but we can treat them all in the same way. And that's by, if you're given an equation, mapping it to y equals mx plus c to allow us to draw a straight line graph so that we can then pull information off that graph and draw conclusions. Let's start with a formula that you're familiar with. V equals IR. This is the Ohms Law Equation. You use this an awful lot in year 12, and it says that the current is directly proportional to the potential difference of the voltage across a wire, as long as temperature and other physical conditions remain constant. And you did an experiment where you gathered different values of V and different values of I and plotted them in a graph. And the graph came out as a straight line through the origin. Then you were able to work out the resistance from that graph by finding the gradient. Why is that? Well, as you know, a straight line through the origin, the graph has the formula y equals mx, where y is whatever's plotted on the y-axis and x is whatever plotted on the x-axis. Now these values, y and x, are usually values that you have gathered in an experiment. So whenever you did this experiment, you gathered values of V and I, and we put those in a more appropriate. Now if we rearrange that equation ever so slightly to V equals R times I, we have now mapped that to Y equals mx, because the V we can plot on the y-axis, the I we can plot on the x-axis, and if we do that, the gradient will equal R. So as I said, that's called mapping an equation to y equals mx. You will have to do this in A-level physics. And what we're going to do is I'm going to eventually give you the equation that links the variables that we measured last time in our experiment and see, can you rearrange that formula to get information from our graph. Let's have a look at another example. This is one of the equations of motion. You might have come across it in physics. You should have come across it in further maths if you've done that. V squared equals u squared plus 2as. Now, an experiment that might use that equation is let's try to find the acceleration of something that is falling. If we have some sort of system with a light gate, and we drop an object, and that object has to drop through a distance s, and it starts from rest, so u equals 0, and the light gate allows us to work out V. We'll be gathering different values of V at different distances s. So let's say we did it at 10 centimetres and 20 and 30. And so you'd have a results table where you'd have values of V and S. So as you changed S, you get different values of V. So we want to map this equation to y equals mx plus c. Now we see we've got a squared here, so really we'd have to square our values of v. And this is going to be our y. This is going to be our x. And we have to fit all the other values in around that. So y equals mx plus c. Let's see if we can fit that in. Well, y is going to be v squared. X is going to be s. Well, m is multiplied by x. In this case, 2a is multiplied by s, so 2a. And then the plus is going to be plus u squared. So y is v squared, x is s. That means that our gradient is going to equal 2 times the acceleration. And so if we plot a graph, and we find the gradient of that graph, we know that that gradient is going to equal 2 times the acceleration. In this case, if we're dropping it from rest, we would expect u to be 0, therefore c should be 0, so we should end up with a straight line through the origin. So if you plot a graph of v squared against s, the gradient is going to equal 2 times the acceleration. What happens if our c value, or our y-intercept, isn't actually 0? This is another equation of motion that you're familiar with. Let's say we are accelerating in a car, and we're going to assume it's a constant acceleration, and we measure the velocity at different times t. So we've now got a table of results at different times and different velocity. Well, what graph should we plot to allow us to work out the acceleration? Y equals mx plus c. Well, v should be our y, x is going to be our t. Don't forget, these values are always going to be the y and the x, or some variation of that. We might have to square something occasionally. M is going to equal a and plus u. So I've rearranged the equation in the form y equals mx plus c, and we can map that. So if we plot a graph, v is going to be in the y-axis, t is going to be in the x-axis, and we should get a graph like that, where the gradient is equal to the acceleration, and the y-intercept is going to equal u. In other words, the velocity when time equals 0, the initial velocity. Right, now I'm going to give you the equation that governs the time period of a pendulum. We have seen that the longer the pendulum, the greater the time period. We saw that it wasn't directly proportional. But this is the equation. Now this is an equation that you're actually going to cover in upper sixth, not lower sixth, but we're going to use it now just for analysis. So you have a results table with different values of L and different values of T. So our X and Y values are going to be based on L and T. Now we have this square root here, and square roots don't really fit into y equals mx plus c. So if you ever see a square root, we're going to square everything. So I'm going to square both sides of the equation. T squared equals, and then 2 pi is 4 pi squared. Then the root L over G turns into L over G. Now I want to get that L by itself, because that L is going to be my X value. T squared equals 4 pi squared over G times L. Looks a bit messy, but that's following the form y equals mx. Where t squared is our y value, and L, the length, is our x value. Y equals mx should give us a straight line through the origin. And we can see now that our gradient should be equal to 4 pi squared over g. So if you have your graph drawn, as it should have been, you've worked out the gradient. Believe it or not, you're now able to work out the acceleration due to gravity. And that's what I want you to do today. I want you to look at the results from the graph that you plotted last week, make sure you have the gradient, and find the acceleration due to gravity. We have mapped an equation to y equals mx plus c. We've plotted a graph based on that equation. In reality, we did that backwards. And now we can use the graph in conjunction with the formula to work out a value, in this case g, the acceleration due to gravity. You know what that should be, so let's see how close you get to your actual value. I'd like you to take a photograph of your graph again with your gradient and your working out to show me what value of g you've got.